In this video, we're going to focus on two-body problems, and by that we mean that there are two bodies that are moving in different ways simultaneously, and then we are asked to find out certain things about the system. For instance, will they actually cross each other? Will they bump into each other? What will the time difference be between them hitting the ground, etc. So starting with this one, two Parklands College pupils try out an experiment on a bridge. One of them allows a stone to fall from rest. Now that's important. That means that the initial velocity is 0 meters per second, and I'm going to call the first stone, stone A. And it falls from rest to the river 122.5 meters below. So the change in position of this stone is 122.5 meters. Her friend throws a second stone. So that means that the stone B is not being let go from her hand, but rather is being propelled from her hand. So when the stone leaves her hand, it is actually traveling at a velocity that is greater than 0 meters per second. It also travels directly downwards, but it's thrown 1 second later, and both stones reach the water at the same time. So there's a lot of information here, and therefore I suggest that one uses two data lists, and this is where data lists and subscripts become especially important. Defining a sign convention, we define down as positive because both stones' initial velocities are downward. So both stones' change in position is plus 122.5 meters. The initial velocity of stone A is 0 meters per second. The initial velocity of stone B is unknown. We will calculate that in 2.2. The acceleration is going to be plus g because gravity acts downward, and we've defined plus as down. So both stones are, once they've left the hands of the two girls, both stones are under the influence of gravity only, so they're in free fall, so they both have the same acceleration. When it comes to the time that stone A travels, we don't know what it is. We call it delta TA. That's the time interval that the stone takes to go from there to there. But we do know that the time interval of stone B is 1 second less. So the first question asks, how long does the stone that is allowed to fall take to reach the water? Now this is not a difficult question. It's not a difficult problem. We are looking at how long does it take for this stone to reach the water. So what we're going to do is we are going to use this equation here. Delta x equals VA delta t plus a half A delta t squared. And you notice I use subscripts A. Using subscripts is not absolutely necessary, but it does help, especially when you get to more difficult problems later on. Substituting in 122.5 for delta xa, and the initial velocity of A is 0, and the acceleration is plus 9.8. And now what I'm going to do is I'm going to explicitly use the fact that delta TA is in actual fact a difference in time between what the time value was at the start of A's motion and what the time value was when it hit the water. You'll see that this delta becomes more important as we do more sophisticated problems. So now, simplifying this, we get 122.5 equals half times 9.8 is 4.9 TA squared. Square rooting that, TA squared equals 25. Square rooting both sides, TA equals 5 seconds. Remember, we cannot get a negative time. So we've now worked out that TA is 5 seconds. So therefore, we'll see that TB is then going to be 5 minus 1, which is 4 seconds. So now 2.2 asks us, calculate the speed with which the second girl threw her stone. So we're now going to look at the second stone, B, in the next slide. So the time interval now of B, as was mentioned, is now 1 second less than for A, because it was thrown 1 second later. Using the same position time equation, once again substituting in the 122.5 for the change in position of B, it falls through the same height, through the same distance from the same height as A. VB initial we don't know. We now know that the time is not 5 seconds but 4 seconds. The acceleration is plus 9.8, 4 squared gives us this equation here, which when taking 78.4 across, we get 44.1. Dividing by 4, we get that VB initial is 11.03 meters per second downwards. 2.3 asks whether it's important that the stones have the same mass. Now, the answer is no. And Galileo proved this when he took two objects of different mass, supposedly two balls, steel balls, if I have the story correct, and dropped them from the Leaning Tower of Pisa, and they both hit the ground, therefore disproving what people had believed for many, many years, that heavier objects fall faster than lighter objects. Just simply isn't true. So using a deeper understanding of what acceleration due to gravity is, and we'll still do this later on in the year, is that gravity, the gravitational acceleration, is actually dependent on a very small constant, universal constant, called the universal constant of gravitation, the mass of the Earth, and the distance from the center of the Earth squared. Now, in this case, both stones are on the same planet and they're at the same distance from the center of the Earth, so their acceleration is not dependent at all on the size or the mass of the stones. So G does not depend on the mass of the stones, so no. Looking at the graphs of motion, we see that over a 5-second interval, stone A travels from 0 meters per second, and it is accelerated at 9.8 meters per second squared, so its velocity is increasing steadily, so it's a straight line, the gradient of which would be 9.8, which is the acceleration. And we see that over a period of 5 seconds, it's going to be accelerated to a final velocity that we didn't work out. It's fine, this is a sketch graph. But it will hit the water 122.5 meters later after it was dropped. Note that because the velocity is initially 0, it has the tangent to this curve is horizontal, and then it steadily increases as it's accelerated until it hits the water. We do not take the effect of the water into account on the stones. We now then look at stone B. Stone B starts its motion 1 second later, and it starts its free fall at a velocity of 11.03 meters per second. It too is accelerated at 9.8, so its gradient of its velocity time graph is the same, therefore these two graphs are parallel. But you can see all the way through that these the two stones are moving they're being accelerated at the same gradient, but they're not moving at the same velocity. And it's only when they get to the water surface that they actually meet up, that they catch up. So the area under this graph which would be a triangle, would ultimately be equal to the area under the trapezium. Therefore, both of the change in positions would be 122.5. Notice that stone B, it starts off with a tangent that's not horizontal, but with a gradient that's actually 11.03, because the gradient of a position versus time graph is the velocity. It doesn't start at 0, and it also has a parabolic shape, and eventually it catches up with the stone that was thrown earlier. Looking at a horizontal two-body problem, a car and a taxi are both traveling with a constant velocity of 20 meters per second along a straight road, with the car 30 meters behind the taxi. The driver of the car realizes the danger he is in, and he decides to overtake. So the car accelerates at a constant rate of 2 meters per second squared. How long will it take before the car is alongside the taxi? Now, this is a classical two-body horizontal problem, and you'll encounter these problems throughout the year in tests and exams. Now, what is critical here is that one defines your problem. You start the problem off correctly. My suggestion to you is that you have two data lists, because the motions of the two objects are different, and that you define a coordinate system. So I've defined the coordinate system such that the x value being 0, the origin is where the car is, and that over time the x value runs to the right, and both vehicles are position, the x value is changing over time. Now at t equals 0, both vehicles have a velocity of 20 meters per second. So their initial velocities are 20 meters per second. I've defined a sign convention where positive is to the right and negative is to the left. Now, both initial velocities are 20. The truck is not going to change its velocity. It's going to continue at a constant velocity, so its final velocity, wherever these two meet up, is still going to be 20 meters per second. So therefore its acceleration is 0, because it hasn't changed its velocity. And the time interval we're going to define as where the two objects, the two vehicles, are next to each other, because remember, car A is going to overtake the truck, it's not going to crash into the truck. That unknown time minus t equals 0 for each of these vehicles is going to be the time interval for those vehicles. Now, at t equals 0, we've defined the car to be at position x equals 0, but that means that the taxi, which is 30 meters in front of the car, is at x equals 30. So the initial position of the taxi is 30. If we had defined the initial position of the taxi to be x equals 0, then this would have had to be x equals minus 3, which would also work, but I prefer not to work with minuses. So now we can move on into the question. How long will it take before the car is alongside the taxi? Well, when the car is alongside the taxi, then the car is at the same x position as what the taxi is, and we're going to use that. So moving now into the problem, we say, well, okay, let's use the position versus time graph, the position versus time equation of motion, this one. Delta x equals delta v, delta x equals v delta t plus a half a delta t squared, and we're going to use it for both vehicles. The change in position of vehicle A is x minus 0. So if we look here, and this is really important, so I'm going to zoom up here, I'm going to move it up here. For the car, when it catches up with the taxi, its change in position is its final position minus its initial position. So its final position is x minus 0. And when I say final position, I mean over this this motion here, where it's trying to catch up with the truck. Obviously not the truck, the taxi, these two vehicles continue, but we're looking at purely at the motion between where the car starts to accelerate and where the car catches up to the taxi. So now, if we now use that, and we substitute the values for the initial velocity, delta t is t minus 0, which is t, plus a half a is plus 2, t squared, because remember delta t is now t minus 0, which is t. Then we get x equals 20t plus t squared. Now this is an equation with two unknowns. So we're going to need another equation. For every unknown you want to solve, you need an equation. So this is the equation of motion for car A. So now let's look at the equation of motion for car B. So the change in position of car B is x minus 30. Remember, it starts at 30. It doesn't start at 0. So each change in position over this time is x minus 30. And that is really, really, really important. This is one of the key things in this problem that you need to take into account, that the change in position of these two vehicles is not the same. So x minus 30 equals 20t, and because the taxi is not accelerating, this term is 0. So this gives us x minus 30 equals 20t, and now we can solve these using a number of different methods. I'm going to use substitution. I'm going to use x equals 20t plus t squared, and I'm going to substitute it into there. You could use elimination. The method you use doesn't matter, as long as it's mathematically valid. So substituting this in for x, 20t plus t squared, minus 30 equals 20t. We can see the 20t's. If you subtract 20t from both sides, they disappear. T squared minus 30 equals 0. Take 30 to the other side. T squared equals 30. Square root both sides. And you get that t equals 5,48 seconds. Now, recall that even though the two vehicles were at different positions at x equals 0, the car is accelerating where the taxi is at a constant velocity. So the time interval is the same for both vehicles, albeit that they don't travel the same displacement in that time. Now, if we substitute that time value back into one of the equations, now I've substituted it into A. I'm taking this and substituting it into there. Then x equals 20 times 5,48 plus 5,48 squared. And so the distance that the car traveled before it overtook the taxi is 139,63 meters. So looking at the graphs of motion, and I've used two different colors to denote the motion of the different motion of the two two vehicles. So taxi B, its initial velocity is 20 meters per second, and over the 5,48 seconds, it maintains its velocity of 20 meters per second, which means that the acceleration of the taxi is 0. Car A is going to accelerate at 2 meters per second squared, which means its gradient for the velocity time graph is going to be 2 meters per second. And we see it accelerates at a constant rate. We didn't work out what the final velocity was there, but that's okay. This is a sketch graph. We were not asked to explicitly work it out. What we did work out is what was the x value for the two vehicles with respect to where the car started off. And so what we do is we say, well, okay, we defined x equals 0 where the car started, and it accelerated. Its gradient of the position versus time graph increased as time went along because the velocity was steadily increasing. But after 5,48 seconds, it was at 139,63 meters from where it started. Taxi B did not start at 0 meters, it started at 30 meters. And so it didn't accelerate, but its change in position was the same per unit time because its velocity was constant. And so its position versus time graph is a straight line. Remember, the gradient of a position time graph gives us the velocity. The gradient of a straight line is constant, so therefore we have a constant velocity graph. We have a horizontal velocity graph. But at the end of the 5,48 seconds, it too is at 139,63 meters with respect to the frame of reference where the car was x equals 0. Let's consider this problem. The driver of a car traveling at night at a speed of 40 meters per second suddenly sees a truck without tail lights which is moving in the same direction. So my sign convention is plus in the direction of the motion of both vehicles, car A and truck B. And once again, I've got two data lists, which I think is essential for doing two-body problems, albeit there's no marks allocated for data lists in an exam or a test. So if you choose to leave it out, that is your prerogative. But as long as you are able to keep track of the different quantities. Now, so the initial velocity of car A is plus 40 meters per second. It says the driver steps on his brakes immediately and the car decelerates at its maximum value of 8 meters per second squared. Now, this is tricky. The car is traveling in a positive direction, but it's decelerating, which means that its acceleration is going to be negative 8 meters per second squared. And the reason for that is that the car's brakes it has a net force which acts in the opposite direction to the direction of the motion. So this must be minus. If the car was exactly 55 meters away, so the car is 55 meters behind the truck, when it started braking, and if the truck was moving at 10 meters per second, determine if the driver avoids an accident. Now, one's got to be careful of these problems because sometimes these problems, the language is a problem. And in this case it is, because it doesn't tell you explicitly that the truck is going to continue to travel at 10 meters per second. But because it doesn't mention that the truck speeds up or slows down, and it doesn't mention anything about the acceleration of the truck, you need to assume that the velocity of the truck is continually 10 meters per second. So I would not say that this is the greatest question for an examination. I think it's a little bit ambiguous. It needs to be a little bit more definite about the fact that the motion of the truck is uniform, it's constant. So now looking at the data table, or the data list, or the data lists of the two vehicles. So we look at car A. We don't know its change in position when it eventually comes to rest, because we need to work that out. We also don't know the change in position of the truck when it comes to rest. We're going to need to work that out. We do know that the truck is not going to accelerate, so it's got a 0 acceleration. Once again, remember I said this is NB, nota bene, important, that minus sign. If you do not put that minus sign in, then you are going to get this problem wrong. And then delta TA and delta TB are unknown. We do not know how long it's going to take for the two to come to rest. We will work that out. So let's look at how long does it take for car A to come to rest. Well, we're going to use this velocity time equation because we are looking for the time when we have the acceleration and the initial and final velocities of the car. The final velocity of the car will be 0 if it's allowed to come to rest and it doesn't bang into the back of the truck. The initial velocity is plus 40. Key, the acceleration is actually a deceleration, so the acceleration is minus 8. The change in time is ta minus 0, where ta is the time it takes for the car to come to rest. All right, now we continue, we work out, we substitute in there, and so we see that minus 8 times ta is minus 8 ta. We take it across, 8 ta equals 40, divide by 8, we get t equals 5 seconds. So how far did car A travel in this 5 seconds? So that's really important. We need to see the distance it's traveled. So using another equation, and yeah, you can use several equations. There's different ways of solving this problem. I'm using this one. V squared, V final squared equals V initial squared plus 2a delta x. V final squared for the car, we're assuming is 0, that it's allowed to come to rest. Its initial velocity is plus 40, its acceleration is minus 8. Its change in position is wherever it comes to rest, xa, minus where it started off. So we see here that it started at 0 and it ended at xa, so that change in position is xa minus 0. So working with that, we see that 40 squared is 1,600. 2 times minus 8 is minus 16xa. Take that across. 16xa equals 1,600. 1,600 divided by 16xa is 100 meters. So it took car A 100 meters before it came to a standstill. So we can understand why it's so critically important to have a following distance. This is a following distance because it took car A 100 meters and 5 seconds before it came to rest. But now what happened to the truck? Now note here, the truck doesn't start at 0 meters in our frame of reference. We have an x-axis here like in mathematics. At t equals 0 for both vehicles, car A is at 0 meters, but truck B is 55 meters in front of car A. Remember, all motion is relative, so you need to describe motion with respect to a reference point. So our reference point we've defined here as x equals 0 when the car starts to decelerate. But what happened to truck B? How far did it travel in the 5 seconds? TB equals TA, because the important thing is, where is the truck when this car actually comes to rest? So looking at this, we see that if we now work this out, we go using delta x equals VB initial delta t plus a half a delta t squared. Now, key, the change in position of the truck is where it lands up, xb minus its initial position. Its initial position was 55, x equals 55 in the frame of reference. Its initial velocity is 10, delta tb is 5, that's determined by the time it takes for the car to come to a standstill. Remember, we want to know where is this truck when the car eventually comes to a standstill. The acceleration of the truck is 0. So therefore xb, take the 55 to the other side, 10 times 5 is 50, xb is 105. So when the car is at 100 meters, the truck fortunately is 5 meters in front. So therefore we can say, yes, the driver stops 5 meters behind the truck in the 5 seconds it takes for his car to come to a standstill. So now I'm going to say something, and I'm going to say this is fine, but you'll see with the graph we need to be careful. We might need to go a little bit deeper into this problem. So looking at the graphs, the truck travels at 10 meters per second consistently over 5 seconds. So its acceleration is 0 meters per second squared. The truck goes from 55 meters to 105 meters. It has a straight line for its position versus time graph. Remember, that's because its velocity is constant. So therefore, the change in position per unit time is the same all the way through. But now the car decelerates. So the car has a deceleration of minus 8 meters per second squared. That was given to us. So it starts at 40 meters per second and it comes to rest over 5 seconds. Now, in science, the more you can understand conceptually, the better. If we just look at this, let's just take 2 or 3 seconds, maybe 5 seconds. After 1 second, it goes from 40 to 32 meters per second. In the next second, it loses another 8 meters per second. So 32 to 24. Okay, 24 to 16. 16 to 8 after 4 seconds, and then to 0. So we can see this is a decelerating velocity time graph. Now, looking at the position versus time graph, we see that the car starts at x equals 0. Remember, the truck started at x equals 55 because it was 55 meters in front of the car. It starts at x equals 0. It starts with a very high velocity, 40 meters per second, so it's got a steep gradient. But then as the vehicle decreases in velocity, the velocity is the gradient of this graph, so the gradient becomes ever so less steep until eventually it's horizontal and it's 0. Now, here is the problem. We are not going to do this, but I'm going to put this as a challenge to you. These are sketch graphs. We have worked out that at 5 seconds, where the car is and where the truck is not in the same place. But is there a possibility that the car actually hit the truck? In other words, that this graph crossed there within the interval between 0 and 5. How would we check that this graph didn't actually cross the truck's graph? Because if it did, big problems. That means that the car actually banged into the back of the truck and therefore there was an accident. So a thorough investigation of this would ensure that we check that this wasn't the case. Now, I'll give you a hint. What you need to do is you need to take the delta x equals v initial delta t plus a half a delta t squared equation of motion and set up an equation for the truck, x versus t for the truck, an equation of x versus t for the car, and then let the x's equal each other, and you're going to get a quadratic equation for the time. Now, you will get a solution. You'll get a mathematical solution. You might even need to use the quadratic formula. If your solution lands up being negative for both t values, then you know that it's not a real solution, and so the car does not bang into the truck. There isn't a time between 0 and 5 where the car and the truck are in the same position. If you do get a value between 0 and 5, then you know that in actual fact the car did crash into the back of the truck. But I leave that for you to explore. So we look at another problem. In this problem, we have a taxi driver who fails to stop for a traffic officer and maintains its full speed of 35 meters per second. Now, I'm going to show you that in some problems, it actually is easier to work with the graphs of motion rather than the equations of motion. So I am going to use a graphical solution here rather than equations of motion. I'm going to leave the equations of motion for you if you would like to do it. But I'm going to show you that graphs are not just something we do in order to test you on them. Graphs can actually really be the best way of actually solving, or the easiest way of solving certain complex problems. So I'm going to start off with the velocity time graph. The taxi is traveling at 35 meters per second. I think us in South Africa, we've seen this time and time again. We get taxis zipping around. And the instant the taxi fails to stop, a traffic officer rushes to his vehicle. So there's a reaction time. Exactly 5 seconds later, the traffic officer pulls off with an acceleration of 8 meters per second squared. Now, it says that the traffic officer maintains this acceleration until he reaches a speed of 40 meters per second. So using our graph, we say, well, okay, 5 seconds later, so this is going to be 0 seconds. So 5 seconds later on our time axis, the motion of the traffic officer in his vehicle starts. We are told that he accelerates from 0 to 40 meters per second. All right, and then he maintains a constant velocity. So you can imagine this traffic officer chasing after the taxi. He's chasing at 40 meters per second, the taxi at 35 meters per second. Eventually, he's going to catch the taxi. The question is, how long does it take for the traffic officer to catch the taxi? And that we're going to define as big T. So let T be the time where the taxi, the change in position of the taxi, all right, and is equal to the change in position of the traffic officer. Now, at T equals 0, this is where our observation of these two objects begins. And when the traffic officer comes alongside the taxi, that's where our observation stops. So using a graph, for a velocity time graph, the change in position of the taxi is the area under that part of the graph. Now that graph is a rectangle. We know its height is 35 meters per second, but the length of it is unknown. It's T, but we want to solve for T, so that's great. So the area is 35 times T, and that area needs to equal the area under the graph of the traffic officer's motion. So I write this equation graphically. So I am now explicitly using the qualities of the graph, the properties of the graph. So we see here this area. Now, okay, what is the base of this area? Well, the base of this area would be T minus 5. The height would be 40 meters per second. Now, this is a trapezium, and we actually would need that side and this side, but we don't have that side either. So what I'm going to do is rather deconstruct this area into a triangle and a rectangle. I'm breaking it up into two simpler areas. The height of the triangle is 40 meters per second. The base of it, well, I'm going to define this point here as little t. All right, and on the side here, I'm going to work out little t. So if we work with this section, here, this point is 5 seconds, 0 meters per second, and the point at the top is t, the t value there, at 40 meters per second. So we know that the gradient is equal to plus 8, because we know the acceleration is 8 meters per second squared. That was given to us in the original statement of the problem, and the acceleration is the gradient of a velocity time graph. So 40 minus 0 is the change in velocity. T minus 5 is the change in time over this time interval there. And so now rearranging this, so 40 equals 8 times t minus 5. We've taken that upstairs. 8 times t, or rather should we divide by 8? 40 divided by 8 equals t minus 5. 40 divided by 8 is 5. Take the 5 across and t equals 10 seconds. So this is 5 seconds, this is 10 seconds. So now that's important, because now we can work out that the base of the triangle is 10 minus 5, which is 5 seconds. So the area there is a half the base, which is 5 seconds, times the height is 40 meters per second. That gives us that the change in position from 5 to 10 seconds is 100 meters. Now, this length here is the base of the rectangle. T is unknown, but we know that's 10. So the length of the base is t minus 10. Times the height of the rectangle is 40. So t minus 10 times 40, we distribute the 40 in to become 40t minus 400. We now then work with the linear equation for t. So we say, okay, we've got 35t equals 100 plus 40t minus 400. 100 minus 400 is minus 300. We take the 40t to the left-hand side to collect the t terms together. 35t minus 40t is minus 5t. Divide by minus 5 on both sides, and we get t equals 60 seconds. So it took 60 seconds from the time that the taxi went past the policeman. Now, must be careful. The time it took for from the time that the taxi passed the policeman, it took 60 seconds. But that means that the policeman was in his vehicle for 55 seconds. But it asks you, how long does it take for the traffic officer to catch the taxi? So one just needs to be careful in the way you answer this. The answer is 60 seconds from the time that he turns around and runs towards his car, towards his vehicle. From the time that he starts to his motion, that would be 55 seconds. So in order to sketch the graphs of motion, I'm going to go a little bit further with this. I'm going to work out what is the actual time, not the time, what is the change in position of the taxi and the policeman at the point where the traffic officer catches up to the taxi. So you're taking this t value and substituting it back into the area of the rectangle for the graph of motion for the taxi, which is 35 times t. 35 times 60 seconds is 2,100 meters. So if one thinks about it, he's traveling at 35 meters per second for 60 seconds. So every second the taxi driver is covering 35 more meters, but over 60 seconds that gives us 2,100 meters. We are going to use these values now to sketch the graphs of motion for the two objects. So we have already sketched this velocity time graph. We have determined that little t is 10 and big T is 60 seconds. Let's look at the acceleration versus time graph. So for the taxi, the velocity is constant, so the acceleration for the taxi is 0 for the full 60 seconds. I should in actual fact put the times in here, 60 seconds, and this is 10. You can see it's definitely not to proportion, but that's okay. This is a sketch, these are sketch graphs, and that's the beauty of sketch graphs. It gives us a basic idea of the shape of the graphs with certain significant points. So now if we look here, we see for the vehicle now, with problems like this, you can get really very, very complicated, because in actual fact, the traffic officer, we don't know what his motion was between when he started to run to the vehicle and how far he was, how fast he ran. So in actual fact, you need to define the boundary of your system. So in actual fact, these graphs is not for the traffic officer per se, but for the traffic officer's vehicle. So I should maybe add to that, this is the traffic officer's vehicle. And this is what we're actually looking at, is the traffic officer's vehicle, not the traffic officer's motion. because that was a little bit more complicated in the first 5 seconds. And we've got no way of knowing how far he was or how fast he ran, whether he's a thin, fast guy or a big guy that had to hobble to the car. But what we do know is that the vehicle was stationary for the first 5 seconds, and then it accelerated. So let's redefine it. We're talking about the motion of the officer's vehicle, which could be a motorbike or it could be a car. So now, if we look at that, and I mention that because sometimes learners get stuck with that because they want to know more information because it worries them. And I know when I was at school also, and to this day I still ask, okay, but what about that? Where's that information? So we need to define the boundary, the limit of our system. We're looking at the taxi's motion and the vehicle of the traffic officer, not the traffic officer's motion in the first 5 seconds. So if we look at the vehicle of the traffic officer's motion, we see that initially it's stationary, so there is no acceleration. Then he accelerates for 5 seconds, from 5 seconds to 10 seconds at 8 meters per second squared. And then when he maintains his constant velocity of 40 meters per second, there's no change in velocity, so the acceleration is 0. So we can see we have like a step function here, a step graph. That's fine. Now, let's look at the position time graph. For the taxi travels at 35 meters per second for the 60 seconds. So the gradient of the position time graph should be a straight line, is constant, so it should be a straight line because the velocity is the gradient of the position time graph. And a constant gradient means that this is a straight line. Remember, y equals mx plus c. The m is a constant for a straight line. Now, what about the traffic officer? Well, the traffic officer's vehicle starts at 0 meters per second, and then he accelerates for 5 seconds. There's a mistake here. Can you see what the mistake is? Well, whilst the vehicle is accelerating, the position versus time graph should be a parabola, which it is, because he starts at 0 meters per second, so it should have a horizontal gradient, and then it should steadily increase, steeper and steeper, because it's increasing in a positive way. The velocity is becoming more positive, so the gradient can become more positive. But here is where I have made a mistake, and the mistake is right here. Because at that point, he stops accelerating. So in actual fact, we need to change the nature of the graph. And so between 10 seconds and 60 seconds, this graph actually needs to be a straight line. It needs to be like this. Because, let me just redraw that, I'm not the greatest at drawing straight lines. And so that needs to be a straight line because of the fact that there is now the gradient of this part of the graph needs to be constant. So that's a parabola and that's a straight line. So you can see how tricky these graphs can become. And there are some recipes that you can use, but at the end of the day, you really got to have an understanding of the basic concepts and of the system. In the next video, we will look at the solution to this problem, and we will then also look at a difficult two-body vertical motion problem, which will come out of a past grade 12 examination paper.